Welcome to Revise and Resubmit, Weekend Classics. I'm Pavlov.
And I'm Nikita.
This week, we're going to be taking a deep dive into Claude Shannon's A Mathematical Theory of Communication.
From 1948.
Yeah, this paper is widely considered the bedrock of the digital age.
Oh, absolutely. It's hard to overstate its impact.
It really is.
Yeah.
I mean, this paper didn't just influence fields like computer science and telecommunications.
Yeah.
It practically created them.
Right.
So where do we even begin with something this monumental?
Well, a good place to start is with the problem that Shannon sets out to solve right at the beginning.
Okay, so what's the fundamental challenge he's tackling?
He defines it as the fundamental problem of communication.
Which is?
Accurately reproducing a message at one point that originated from somewhere else.
Okay, so think like sending a text message.
Exactly.
Or making a phone call.
Or even just talking face to face.
Right. It all boils down to transmitting information from one point to another.
Exactly.
And that's where Shannon's genius really shines through. He separates the meaning of a message from the engineering problem of transmitting it.
That's right. He's not concerned with what you're saying, just with ensuring that whatever you say gets to the other side intact.
So it's like he's saying, I don't care if you're sending a love letter or your grocery list. I just want to make sure it gets there without any typos.
Exactly.
Okay, I like that analogy. And that's where this revolutionary concept of bits comes in, right?
Exactly. A bit is like a fundamental unit of information.
Okay.
Representing a choice between two possibilities.
Like a light switch, on or off, 0 or 1.
Exactly. And you know those massive files you download like movies or games?
Oh, yeah?
They're nothing but billions of these tiny bits strung together.
That's incredible. Mm-hmm. It's mind-blowing how much information we can pack into these simple on-off switches. So how does Shannon actually break down the process of communication?
He breaks down a communication system into 5 key parts.
Okay, let's hear it.
You have the source of the message,
Okay.
the transmitter that encodes it, the channel it travels through, the receiver that decodes it, and finally the destination.
So essentially the journey of a message from start to finish.
Precisely.
And this model is so powerful because it applies to almost any form of communication, right?
Exactly.
From smoke signals to fiber optic cables, it all boils down to these 5 components.
Right. And it's this model that allows us to analyze and improve how we transmit information.
Now, this is where things start to get really interesting. For me, at least, Shannon compares written language like English to mathematical processes.
Yes, he does.
He uses probability theory, like you might remember from flipping coins in math class,
Right.
to analyze the structure of language.
That's right.
And here's where he goes a step further. He actually creates models of English text using math.
He does. It's amazing.
He starts with gibberish, and by adding more statistical rules, gets surprisingly close to real English.
Right.
It's like he's teaching math to speak English.
I love that analogy.
These models capture things like the frequency of letters, and even common letter combinations like the or ing.
It's remarkable.
It really is. It's a powerful demonstration of how even something as complex as language can be analyzed and understood using mathematical tools. So, okay, let's talk about entropy.
Yeah.
It's a measure of uncertainty, or how much surprise there is in a message.
Right.
A random string of letters has high entropy,
Yes.
while a predictable sentence has low entropy.
Think of it this way. A message with no surprises has 0 entropy.
Gotcha. So how does knowing the uncertainty of a message help us communicate better?
Well, entropy limits how efficiently you can compress a message.
Meaning?
You can't squeeze more information into a given channel than its entropy allowed.
So it's like trying to stuff a giant suitcase into a tiny backpack.
Exactly.
It's just not going to fit.
Right.
And this understanding of entropy is crucial for developing efficient coding schemes, which is essential for transmitting information quickly and reliably. Now, to really grasp Shannon's contribution, I think we need to delve into the structure of his paper a little bit.
Okay, sounds good.
So how's it organized?
The paper is divided into 2 main parts.
Okay. Dealing with discrete and continuous information.
Okay, so tell me about the first part.
The first part is titled Discrete Noiseless Systems.
Discrete noiseless systems.
Yes. This section lays the groundwork.
Okay.
Imagining a channel where data is transmitted as discrete symbols without any errors.
So kind of a perfect world scenario.
Exactly. It's a simplified model, but crucial for understanding the fundamentals.
So it's like sending Morse code, dots and dashes, representing letters with no static or interference.
Exactly. A perfect world scenario.
Okay. And then what?
Then he dives into the discrete source of information.
Okay, so he's getting a little more specific now.
Right. Here, Shannon models the source of information as a stochastic process, which essentially means a system with randomness or unpredictability.
Okay, I'm following.
This is key because real-world information, like human language, is not perfectly predictable.
Right. It's like trying to predict the weather. You can look at patterns and make forecasts.
Exactly.
But there's always some element of randomness involved.
Right.
So what comes next in the paper? Next up, the series of approximations to English.
Ooh, that sounds interesting. Tell me more.
This is where Shannon gets really creative. He develops increasingly accurate models of written English using probabilistic methods.
All right.
These models start simple, with each letter having an equal probability, and gradually become more complex.
Incorporating things like
Delarogram and even word frequencies.
so like actual usage patterns.
Exactly. It's fascinating to see how these mathematical models begin to resemble real English text.
It's like watching a computer learn to speak our language one statistical rule at a time.
Right.
Fascinating.
Yeah.
Okay, so then what?
Then he gets into graphical representation of a Markov process.
Okay, so he's bringing in some visuals now.
Right. He uses graphs to visually represent these models.
So think like a flow chart, showing how likely one letter or word is to follow another.
Exactly.
This helps us understand the structure and dependencies within language, even capturing things like grammatical rules implicitly.
It's quite powerful.
Okay, so he lays out the groundwork with these models, and then what?
The paper then goes on to explain ergodic and mixed sources.
Ergodic and mixed sources. Okay, break that down for me.
This section delves into different types of sources and their properties.
Okay.
Ergodic sources have a kind of statistical consistency, meaning if you take a long enough sample of their output, it'll accurately reflect the overall probabilities of the source.
Gotcha.
Mixed sources are combinations of different ergodic sources, which adds more complexity. Imagine mixing different languages or styles of writing together.
Okay. I could see how that would make things more challenging.
Right.
All right, so we're moving through the paper here. What comes next?
Next, choice, uncertainty, and entropy.
Okay, so we're circling back to entropy now.
Right. This is where Shannon formally introduces the concept of entropy as a measure of information content.
And how does he go about doing that?
He demonstrates how to calculate entropy based on the probabilities of different messages occurring.
So a message with no surprises has zero entropy.
Exactly.
And then what?
Then we come to the entropy of an information source.
Okay, so building on that foundation.
Right. This section explains how to calculate the entropy of a source based on the probabilities of its different states and the messages it produces.
So it's like measuring the flow rate of information from a source.
Exactly. A great way to think about it.
Okay, and then what?
Then he focuses on representation of the encoding and decoding operations.
Okay, so we're getting into the nuts and bolts of how information is actually transmitted and received.
Exactly. This section gets into the nitty-gritty of how we actually represent information for transmission and then decode it back at the receiving end.
Okay, so let's talk about that.
He introduces the concept of a transducer, which is a mathematical model for any device that transforms information like an encoder or decoder.
So think of it like a translator.
Exactly, converting information from one form to another.
Okay, and what comes after that?
He goes on to discuss the fundamental theorem for a noiseless channel.
Okay, this sounds important.
This is a key result in Shannon's theory. It essentially says that you can encode a message from a source to transmit over a noiseless channel at a rate arbitrarily close to the channel's capacity without losing any information.
So we can achieve near perfect compression as long as we're willing to accept some delay.
It's like saying you can fit that giant suitcase into the tiny backpack if you're willing to take your time and pack it really, really carefully.
Right. Okay, I'm with you. So we're nearing the end of the first part here. What's next?
What follows is discussion.
Okay, so he's taking a step back now and looking at the bigger picture.
Right. Here, Shannon reflects on the broader implications of his findings,
Such as.
emphasizing the importance of matching the source to the channel for efficient communication.
So it's like tailoring your message to fit the medium perfectly.
Exactly.
Makes sense.
He also points out that even in real-world scenarios where noise is inevitable, some level of redundancy in the source can actually be helpful in combating errors.
Interesting. Okay, and finally to wrap up the first part.
Finally, he closes the first part with examples.
Okay, so he's giving us some concrete applications of his theories.
Right. Shannon provides some concrete examples to illustrate his ideas.
For example.
For instance, he shows how to efficiently encode a message from a source that produces letters with certain probabilities, using binary digits. This demonstrates how to achieve practical compression by cleverly assigning shorter codes to more frequent symbols.
Smart.
He also hints at the possibility of adapting the encoding scheme based on the characteristics of the channel.
Okay.
Like the level of noise present.
So it's like choosing the right language for the right audience.
Exactly.
Okay, so that wraps up the first part of Shannon's groundbreaking paper. A mathematical theory of communication. Stay tuned as we dive into the second part where things get even more interesting.
All right, so now we move on to the second part of the paper.
Yeah.
Where things get even more interesting.
Lay it on me.
The discrete channel with noise.
Ah, yes, noise, the bane of any good signal.
Exactly. Real-world communication channels are never perfectly noise-free.
There's always some interference out there.
Always, whether it's static on a phone line
Right.
or errors introduced during data transmission.
So how do we deal with this inevitable noise? I mean, it's everywhere.
Well, Shannon tackles this head-on.
Okay.
He first explains how to represent a noisy channel mathematically,
Okay.
using probabilities
Uh-huh.
to describe how likely a transmitted symbol is to be received,
Okay.
correctly or incorrectly.
So there's like a 1% chance that a 1 gets flipped to a 0
Precisely.
because of some electrical gremlins or something.
Yeah, and this leads to two really crucial concepts.
Okay.
Equivocation and channel capacity.
Okay, remind me again, what's equivocation?
Equivocation measures how much uncertainty remains about the original message after it's been received through a noisy channel.
Okay.
It's essentially the information lost due to that pesky noise.
So a high equivocation means we're basically playing a guessing game
Yeah.
about what was actually sent.
Shannon gives a great example to illustrate this.
Have a game, I'm listening.
Imagine you're sending a stream of zeros and ones, and 1% of the bits get flipped because of noise.
Right,
You might think you're transmitting at 99% efficiency,
right. Just subtract the error rate
but that doesn't take into account the receiver's uncertainty.
because they don't know which bits were flipped.
Exactly. They don't know which bits were flipped.
Gotcha.
This uncertainty is what equivocation captures.
So how does this tie into channel capacity then?
Channel capacity is the maximum rate at which you can reliably transmit information through a noisy channel.
Okay.
It's the rate where you can make the equivocation arbitrarily small,
Okay.
meaning you can be as certain as you want about the original message
Okay.
by using clever coding techniques.
Wow, so even with noise, there's a fundamental limit
Yes.
to how much information we can squeeze through.
Exactly. And Shannon proves this in his fundamental theorem for a discrete channel with noise.
Okay.
It states that if the entropy of your source, the rate at which it produces information,
Right.
is less than the channel capacity,
Yeah.
you can transmit with an arbitrarily small error rate.
So we can get as close to perfect transmission as we want,
Oh,
even with noise, as long as we stay below the capacity limit.
you got it. Now, if you try to exceed the capacity,
Oh.
you'll inevitably pay the price in increased equivocation.
Meaning more uncertainty about the received message.
Right. It's like nature is saying not so fast.
So basically, this theorem is giving us a speed limit
Exactly.
for reliable communication over a noisy channel.
It's a profound result.
Right.
With huge implications. It tells us that noise doesn't completely destroy our ability to communicate reliably.
Okay.
We just need to adapt our encoding strategies to account for it.
And this leads into what I find to be a really fascinating discussion
Yes.
about how to practically deal with noise.
Right. Shannon doesn't give us a specific recipe for
Okay.
optimal coding, but he outlines the key principles.
Okay.
The idea is to introduce redundancy in a way that combats the specific noise characteristics
Okay.
of the channel.
So it's not just about repeating the message over and over again.
No.
But adding redundancy in a clever way.
Exactly.
Yeah.
Think of it like sending a package
Okay.
through a really rough postal service.
Yeah.
You wouldn't just throw a fragile item in a box and hope for the best.
You'd carefully pack it with bubble wrap
Exactly.
and padding tailored to protect it
Right.
from the specific bumps and jostles it's likely to encounter.
That's a great analogy. So is this where things like error correcting codes come in?
Yeah, like checksums and stuff.
Precisely. These codes add extra bits to the message
Okay.
in a structured way, allowing the receiver to detect and correct errors
Right.
introduced by the noise. It's kind of like adding checksums to data packets
Gotcha.
to ensure their integrity.
So Shannon's theory not only gives us the theoretical limits,
Right.
but also guides us towards practical ways
Yes.
to approach reliable communication
Exactly.
in a noisy world.
That's one of the things that makes this paper so remarkable.
Right.
It's both deeply theoretical and intensely practical.
So let's break down this section further.
Okay.
He gives us an example of a discrete channel and its capacity.
Right here, he works through a specific scenario.
Okay.
Where you have a channel with 3 symbols and a particular noise model. By carefully choosing the probabilities of using each symbol.
Okay.
He shows how to maximize the channel capacity.
Okay.
This demonstrates how matching the source statistics to the channel characteristics can lead to optimal communication rates.
Okay. And then he moves on to the channel capacity in certain special cases.
Right. This is where Shannon explores how to calculate channel capacity for channels with specific noise structures.
Okay.
He considers cases where noise affects symbols independently and derives a set of equations for finding the optimal probabilities for using different symbols. This provides a practical toolbox for engineers designing communication systems.
Right, for various types of noise environments.
Okay, it's really useful stuff.
And finally, for this section, he gives us an example of efficient coding.
All right, let's hear it.
Where he demonstrates, with a hypothetical example, how to create a code that achieves the theoretical limit of channel capacity, allowing for perfect error correction.
It's like finding a way to have a crystal clear conversation.
Exactly.
Even in the middle of a noisy party.
His insights from 1948 are still the foundation of how we communicate in the digital age.
Okay, so we've tackled discrete information, but what about continuous signals?
Right, that's where the second half of Shannon's paper takes us.
This is where we move from bits and symbols to things like audio and video.
Exactly. Instead of distinct dots and dashes, we're dealing with smooth, continuous waves.
So think of a sound wave. It's constantly changing with no clear-cut breaks.
Right.
So how do we even begin to measure information in something like that? It seems like a completely different beast. Well, that's where Shannon's ingenuity comes in again.
Okay.
He connects continuous signals to their frequency spectrum.
Frequency spectrum, no, that rings a bell from physics class.
Right. It's all about breaking down a complex signal into a bunch of simpler sine waves of different frequencies.
Okay, I vaguely remember that. But how does that help us measure information?
Shannon realized that the wider the frequency spectrum of a signal, the more potential it has for carrying information.
So a signal with a narrow bandwidth is like a limited vocabulary, while a wide bandwidth gives you a whole dictionary to play with.
That's a great way to put it. And this insight leads to the famous Shannon-Hartley theorem.
All right, this sounds important. Lay it on me.
The Shannon-Hartley theorem gives us a formula to calculate the capacity of a continuous channel with noise.
Capacity meaning the maximum rate we can send information reliably.
Exactly. And it says that capacity depends on 2 things: the bandwidth of the channel and the signal-to-noise ratio.
So wider bandwidth, stronger signal, more information we can squeeze through. Makes sense.
Right. This theorem underpins modern communication systems.
I can see that.
It tells engineers how to design for optimal data rates given the constraints of the channel.
It's why we've seen such a massive growth in data-hungry applications.
Exactly.
Like streaming video and high-speed internet.
Imagine trying to watch Netflix with dial-up speeds.
Oh, the horror.
Thanks to Shannon-Hartley, those days are long gone.
But dealing with continuous signals brings up new challenges, right? It's not as simple as just mapping symbols to bits anymore.
Right, you can't just chop a continuous wave into discrete chunks without losing something in the process.
So how do we bridge that gap?
Shannon introduces the idea of quantization.
Okay.
It's essentially dividing the continuous signal into discrete steps.
Kind of like rounding off numbers.
Precisely. It's like saying instead of having every possible shade of blue, we'll group them into a set of specific shades.
But doesn't that mean we're losing some information?
There's always a trade-off.
Right.
But with clever quantization techniques, we can minimize the loss to the point where it's practically unnoticeable.
So when I listen to my digital music, it's not a perfect replica of the original sound waves.
That's right.
There's some rounding going on behind the scenes.
But the magic of Shannon's work is that it gives us the tools to do this rounding in the smartest way possible, preserving the essence of the signal.
So we get the convenience of digital without sacrificing too much fidelity.
Exactly. And Shannon provides the mathematical framework to make this happen.
It's incredible how this one paper touches on so many aspects of our digital lives.
It really is. And it goes even further.
Oh.
He explores really forward-thinking concepts like communicating over a channel with unknown characteristics.
Wait, how can you communicate effectively if you don't know anything about the channel? That sounds like shooting in the dark.
It does seem impossible, but Shannon shows it can be done with advanced coding techniques.
So it's like navigating a maze blindfolded.
In a way, this has huge implications for things like wireless communication, where the channel can change unpredictably.
Makes sense. Signals bouncing around, interference popping up, you need to be adaptable.
Exactly, and Shannon's work provides the theoretical foundation for making that adaptability possible.
So after this deep dive into Shannon's communication, why should our listeners care about this work today, almost 80 years after it was published?
His insights are more relevant than ever. They laid the groundwork for the digital revolution. We have the internet, smartphones, streaming services, all thanks to the foundation he laid.
It's not just about the technology either.
It's about how we think about information itself. Shannon gave us a way to quantify it, to measure it, to manipulate it mathematically.
That's a powerful legacy.
His work continues to inspire research and innovation. As we push the boundaries of communication, exploring things like quantum computing and interstellar communication, Shannon's ideas remain a guiding light.
He truly set the stage for the information age. If you enjoyed this deep dive, we encourage you to check out the original paper. Be warned, though it's a dense read.
But there are plenty of great resources online that offer a more accessible overview of information theory.
And of course, don't forget to subscribe to Revise and Resubmit, Weekend Classics on Spotify and Apple Podcasts.
We'll be back next week with another classic paper, breaking down complex research into digestible insights.
Until then, keep those neurons firing.